The James Webb Space Telescope has been sending back images for less than 3 years. 3 years, that's it. And in that impossibly short amount of time, it's already fundamentally changed our understanding of the universe. But there's one discovery that stands above all the others, one finding that's so shocking, so completely unexpected, that it's forcing astronomers to rewrite textbooks that have been standard for decades. And it's not about exoplanets or black holes or even the edge of the observable universe. It's about stars, regular, ordinary stars, suns like our own sun. We thought we knew how many there were. We thought we understood where they came from and when they formed. We thought we had the cosmic census pretty much figured out. We were wrong, spectacularly, incredibly wrong. James Webb didn't just find a few more stars than we expected. It didn't find twice as many or even 10 times as many. What it found is so far beyond our predictions that astronomers initially thought the data had to be corrupted. They ran the numbers again and again and again. The data was correct. The universe is absolutely flooded with stars in places and times we never thought possible. Galaxies that shouldn't exist are bursting with stellar formation. Eras of cosmic history we thought were dark and empty are blazing with the light of billions of suns. And the implications? They are staggering. Because if we were this wrong about something as fundamental as stars, what else have we gotten wrong about the universe? This is what James Webb just found, and it changes everything. Section 1, the telescope that sees the impossible. Let's start with the telescope itself, because you need to understand just how revolutionary this instrument is to appreciate why its discoveries are so shocking. The James Webb Space Telescope launched on Christmas Day, 2021. It had been in development for over 25 years. It cost about $10 billion. It was the most expensive, most complex, most ambitious space telescope ever built. And if anything had gone wrong during its deployment, the entire mission would have been a complete failure. There was no backup plan, no way to repair it, no second chances. The tension during those first few weeks was unbearable for the scientists involved. Webb had to execute a series of about 300 single-point failures, 300 different mechanisms that all had to work perfectly, or the whole telescope would be useless. It had to unfold in space like an origami masterpiece. It had to deploy a tennis court-sized sun shield. It had to align 18 separate mirror segments into one perfect surface. Any one of those things could have failed, and if they had, we'd have lost a decade of work and $10 billion. But they didn't fail. Everything worked. Against all odds, every single deployment mechanism functioned exactly as designed. The sun shield unfurled, the mirrors aligned, the instruments calibrated, and then it started looking at the universe. James Webb doesn't see visible light like our eyes do, or like the Hubble Space Telescope does. It sees infrared radiation, heat. This is crucial. This is why it can do things Hubble could never do. Infrared light has longer wavelengths than visible light. This means it can pass through dust clouds that block visible light. More importantly, it can see objects that are so far away that their light has been stretched by the expansion of the universe into the infrared spectrum. This is called redshift. When light travels across billions of light years of expanding space, its wavelength gets stretched. Blue light becomes red light. Red light becomes infrared. The farther away something is, the more its light is redshifted. Hubble could see some infrared, but not much. Its sweet spot was visible and ultraviolet light. This limited how far back in time it could see. There was a wall, a point beyond which the universe was effectively invisible to Hubble, because all the light from that era had been redshifted too far into the infrared. James Webb smashes through that wall. It can see infrared light that's been traveling for over 13 billion years. It can see the universe when it was less than 400 million years old, just 3% of its current age. To put that in perspective, if the universe's current age of 13.8 billion years were compressed into a single year, James Webb can see back to January 11th. Hubble could barely see past mid-February. That extra month might not sound like much, but in cosmic terms, it's everything, because that's when the first stars were forming. That's when the first galaxies were assembling. That's when the universe was transitioning from a dark, formless void into the brilliant, structured cosmos we see today. And what James Webb found when it looked at that early universe is absolutely stunning. Section 2, the impossible galaxies. The first shocking images came back in July 2022, just a few months after Webb became operational. NASA released what they called the Deep Field Image, a photo of a tiny patch of sky, no bigger than a grain of sand held at arm's length. In that tiny patch, Webb found thousands of galaxies, thousands, each one containing billions or even trillions of stars. Galaxies so distant that their light has been traveling toward us for over 13 billion years. But here's what made astronomers' jaws drop. These galaxies were huge, massive, fully formed. They had spiral arms and central bulges, and all the structures we associate with mature galaxies. They looked like galaxies that should be billions of years old, except they couldn't be billions of years old, because the universe itself was only a few 100 million years old. At the time we're seeing them, this shouldn't be possible. According to every model of galaxy formation we had, early galaxies should be small and chaotic. They should be irregular blobs of stars, not grand spirals and elegant ellipticals. They should still be in the process of assembling, not already mature and structured. Think of it this way. It's like looking at ultrasound images of a 1-month-old embryo and finding a fully formed teenager. It violates everything we understand about how development works. The scientific papers started coming out. Titles like "A Population of Red Candidate Massive Galaxies at Z greater than 10 with JWST," and "A Massive Quiescent Galaxy at Redshift 4.658. Dry, technical language that barely conceals the shock underneath. Redshift 10, Redshift 12, Redshift 14. These numbers represent distances and times so extreme that they were purely theoretical before Webb. We thought maybe, just maybe, we might find a few tiny protogalaxies at those distances. Instead, we found massive, mature galaxies everywhere we looked. Astronomers started calling them Webb's impossible galaxies. Some scientists wondered if the data was wrong, if maybe the distance measurements were off. But the measurements kept checking out. The spectroscopy confirmed it. These galaxies really were that distant, really were that early, and really were that massive. One galaxy, dubbed JWST 214-0, appears to exist just 290 million years after the Big Bang. It contains hundreds of millions of stars. It's actively forming new stars at a rate that would have been impressive for a galaxy billions of years old. And it has complex chemical signatures that indicate multiple generations of stars have already lived and died. Let me emphasize this: multiple generations of stars, born, lived, exploded as supernovas, and seeded the galaxy with heavy elements, all within the first 290 million years of cosmic history. For context, our own sun is only on its first generation. It formed about 4.6 billion years ago from a cloud of gas and dust that contained elements from previous stars. Yes, but the sun itself is still in its main sequence, still happily burning hydrogen into helium, and will continue doing so for another 5 billion years or so. These early galaxies were cycling through stellar generations like they were on fast forward, and nobody can fully explain why. Section 3, the stellar baby boom. But the impossible galaxies were just the beginning. As Webb continued its observations, as more data came in and more analysis was done, a pattern started to emerge. And this pattern is what really changes everything. The early universe was making stars at an absolutely furious rate, far more than our models predicted, and not just in a few special places, everywhere. Every early galaxy Webb looked at was blazing with stellar formation. Astronomers measure star formation rates in solar masses per year. Our Milky Way galaxy currently forms about 1 to 2 solar masses worth of new stars every year. That's pretty typical for a mature galaxy. Some galaxies make more, some make less, but 1 to 2 solar masses per year is the ballpark. These early galaxies, they're forming stars at rates of 100, 200, even 300 solar masses per year. Some measurements suggest rates even higher. They're producing new stars at rates 100 to 200 times faster than the Milky Way. And there are a lot of them, way more than there should be. Before Webb, we estimated there might be a few dozen galaxies in the entire observable universe at redshifts greater than 10. We thought the early universe was sparsely populated, with only a handful of proto-galaxies beginning to form. Webb has found hundreds of galaxies at those distances. Hundreds. And those are just in the tiny patches of sky it's surveyed so far. Webb has looked at maybe 0.001% of the entire sky. If the pattern holds across the whole universe, we're talking about millions of these early, massive, star-forming galaxies. Do the math. If each one is forming stars at 100 plus solar masses per year, and there are millions of them, the early universe was producing new stars at a rate that's almost incomprehensible. Billions upon billions of suns being born every year across the infant cosmos. This is the stellar baby boom, and it's completely rewriting our understanding of cosmic history. Here's why this matters. Stars are the building blocks of everything. They're not just pretty lights in the sky, they're cosmic factories that create every element heavier than hydrogen and helium. Carbon, oxygen, nitrogen, iron, gold. Every atom in your body that's not hydrogen was forged in the core of a star or in the explosion of a supernova. If the early universe was making stars at these incredible rates, it was also creating heavy elements much faster than we thought. This changes our understanding of when planets could form, when life could potentially emerge, when the universe became chemically complex enough to support the kind of chemistry we see today. It also means the early universe was much brighter than we thought. All those stars pumping out light, their radiation ionizing the hydrogen gas that filled space, creating bubbles of ionized gas that eventually merged to make the universe transparent. We thought this rionization process took hundreds of millions of years. Webb's data suggests it might have happened much faster, driven by this intense burst of stellar formation. Section 4. Where did all these stars come from? Okay, so we've established that the early universe had way more stars than we expected, forming way faster than we predicted, in galaxies that were way more massive and mature than they should be. The obvious question is, why? What caused this stellar baby boom? And more importantly, why didn't we predict it? To answer that, we need to understand how stars form. And this is where things get complicated, because star formation is one of the most complex processes in astrophysics. Stars form from clouds of gas and dust. These clouds exist in galaxies, floating between existing stars. Most of the time, they're stable. Gravity tries to pull them together, but gas pressure and turbulence and magnetic fields push back. The cloud just sits there, not doing much. But sometimes something triggers collapse. Maybe a nearby supernova sends a shockwave through the cloud. Maybe two clouds collide. Maybe the cloud just gets dense enough that gravity finally overwhelms the other forces. For whatever reason, parts of the cloud start to collapse. As the gas collapses, it heats up. It spins faster. It fragments into clumps. Each clump continues collapsing. Eventually, if a clump gets dense and hot enough, nuclear fusion ignites in its core. A star is born. This process is well understood in the modern universe. We can see it happening in star-forming regions like the Orion Nebula. We have detailed computer simulations that match observations beautifully. But the early universe was different. Fundamentally, chemically different. Right after the Big Bang, the universe contained only hydrogen and helium. That's it. Literally nothing else except trace amounts of lithium and beryllium. No carbon, no oxygen, no silicon, no iron, none of the elements that make up planets and rocks and, well, you. These heavy elements, astronomers call anything heavier than helium a metal, in a linguistic quirk that drives chemists crazy. These metals are crucial for star formation. They help gas clouds cool down. When gas cools, it can collapse more easily. More collapse means more stars. The first generation of stars, called population 3 stars, had to form from pure hydrogen and helium. No metals to help the gas cool. This should have made star formation harder, slower, less efficient. And because these first stars had no metals, they should have been massive. Really massive. Hundreds of solar masses. These monster stars would burn incredibly hot and bright, fusing hydrogen into helium and then into heavier elements in their cores. They would live fast and die young, exploding as supernovas and seeding the universe with the first heavy elements. These metals from the first generation would make it easier for the second generation to form. Stars could be smaller, more diverse. Galaxies could start assembling from the gravitationally bound clouds of gas. This is the theoretical framework we had. This is what the computer models predicted. The first few 100 million years should be a slow, inefficient process of forming massive population 3 stars, having them explode, gradually enriching the universe with metals, and only then starting to see the kind of robust star formation we observe in later eras. But that's not what Webb is seeing. Webb is seeing massive star formation starting incredibly early. Not a slow ramp-up, but an explosion of stellar birth right out of the gate. Either our models of star formation are wrong, or something else was going on in the early universe that we don't understand. Section 5. The dark matter mystery. Here's where we need to talk about dark matter, because it might be the key to understanding why the early universe had so many stars. Dark matter is one of the biggest mysteries in astrophysics. We know it exists because we can see its gravitational effects. Galaxies spin too fast. The outer stars are moving so quickly that they should fly off into space, but they don't. Something is holding them together with extra gravity. Galaxies in clusters move around each other in ways that only make sense if there's way more mass than we can see. Light from distant galaxies bends around foreground galaxies more than it should, based on visible matter alone. All of this evidence points to the existence of matter that doesn't interact with light. It doesn't emit light, doesn't absorb light, doesn't reflect light. It's completely invisible. All we can detect is its gravity, and there's a lot of it. About 85% of all matter in the universe is dark matter. The stuff we can see, stars, planets, gas clouds, you, me, makes up only about 15% of the total matter. We're the minority. The universe is dominated by something we can't see and don't fully understand. Now, here's the connection to star formation. Dark matter creates the gravitational scaffolding that allows normal matter to collect and form structures. In the early universe, dark matter started clumping together first. It wasn't affected by radiation pressure or gas pressure, so it could start forming gravitational wells, while normal matter was still too hot and diffuse to collapse. These dark matter halos pulled in normal matter, hydrogen and helium gas. The gas fell into the gravitational wells created by dark matter, creating concentrations dense enough for stars to form. So the distribution and behavior of dark matter directly controls where and how fast galaxies can form. More dark matter, concentrated in denser halos, means more places for gas to collect and more stars to form. Current models of dark matter predict a certain distribution of halos in the early universe. Based on those predictions, we calculated how many galaxies should exist at different times and how massive they should be. Webb's observations don't match those predictions at all. There are several possibilities here. First, maybe our models of how dark matter behaves are wrong. Maybe dark matter clumps together more efficiently than we thought, creating more and denser halos in the early universe. This would provide more sites for galaxy formation and explain the abundance of early galaxies. Second, maybe the connection between dark matter halos and visible galaxies is different than we assumed. Maybe normal matter was more efficient at falling into dark matter halos and forming stars in the early universe. Maybe there's some process we don't understand that accelerated star formation. Third, maybe there's something about dark matter itself that we're missing. Maybe it interacts with normal matter in subtle ways we haven't detected. Maybe there are multiple types of dark matter with different properties. Any of these possibilities would require major revisions to our current models. And that's what makes this so exciting and so unsettling at the same time. Section 6. The measurement problem. Before we go further, we need to address a crucial question. How sure are we that these observations are correct? Could there be errors in the measurements? Could we be misinterpreting the data? This is a legitimate concern. Extraordinary claims require extraordinary evidence, and claiming that our fundamental models of galaxy formation are wrong is about as extraordinary as it gets. So let's talk about how astronomers measure distances in space, because that's crucial to understanding whether these galaxies really are as early and as massive as they appear. For relatively nearby objects, we can use parallax, the apparent shift in position as Earth orbits the Sun. This works for stars within a few thousand light years. For more distant objects, we use standard candles, objects whose intrinsic brightness we know. If we know how bright something actually is, and we measure how bright it appears from Earth, we can calculate how far away it must be. Cepheid variable stars and Type 1a supernovas are the most common standard candles. But for the most distant galaxies, these methods don't work. We have to use redshift. Remember how I explained earlier that light gets stretched as it travels through expanding space? The amount of stretching tells us how much space has expanded since the light was emitted, which tells us how long ago it was emitted, which tells us how far away the object is. Redshift is measured by looking at spectral lines, specific wavelengths of light emitted or absorbed by different elements. Hydrogen, for instance, emits light at very specific wavelengths. If we see those hydrogen lines shifted toward redder wavelengths, we know the object is moving away from us due to cosmic expansion. The amount of shift tells us the redshift value, usually denoted as Z. A redshift of Z equals 1 means wavelengths are stretched by a factor of 2. Z equals 2 means stretched by a factor of 3. Z equals 10 means stretched by a factor of 11. These ultra-distant galaxies Webb is finding have redshifts of Z equals 10, ZT equals 12, even Z equals 14 or higher. This is in the realm where Hubble could barely function, where ground-based telescopes are completely blind. But here's the thing. Spectroscopy takes time. You need to collect enough light to see those spectral lines clearly. For faint, distant galaxies, this can take hours or even days of observation time. And telescope time on Webb is precious. There's a waiting list of scientists who want to use it, proposals that have to be reviewed and approved. So for initial surveys, astronomers often use photometric redshifts instead of spectroscopic redshifts. This means looking at the galaxy's brightness in different wavelength filters and using that to estimate the redshift. It's faster but less precise. Some of the early impossible galaxy discoveries were based on photometric redshifts. And this led to some skepticism. Maybe, critics said, these aren't really Z equals 10 plus galaxies. Maybe they're lower redshift galaxies that just happen to have colors that make them look more distant than they are. It's a valid concern. Photometric redshifts can be wrong. There are known sources of error. But as more data has come in, as spectroscopic follow-up observations have been done on some of these galaxies, the results have held up. These galaxies really are that distant. The redshifts are confirmed. JWST 14-0. That galaxy at Z equals 14 I mentioned earlier, that's a spectroscopically confirmed redshift. They took the time to get a detailed spectrum. The measurement is solid. more and more of these early galaxies are getting spectroscopic confirmation, and they keep turning out to be just as distant as the photometric estimates suggested. If anything, some are even more distant than initial estimates. So the measurement problem isn't the answer. These galaxies are real. They're really that early in cosmic history, and they really do challenge our models. Section 7. What this means for the cosmic census. Let's zoom out for a moment and think about what this means for our understanding of the universe as a whole. Because we're not just talking about a few anomalous galaxies. We're talking about a fundamental reassessment of the cosmic census. How many stars exist, where they are, when they formed. Before James Webb, astronomers estimated there were about 200 billion galaxies in the observable universe. This number came from deep surveys, like the Hubble Ultra Deep Field, extrapolated across the entire sky. Each galaxy contains, on average, about 100 billion stars. Some have more, some have fewer, but 100 billion is a reasonable middle estimate. Do the math. 200 billion galaxies times 100 billion stars each equals 20 sextillion stars. That's 20 quintillion stars. A number so large it's essentially meaningless to human comprehension. That was our best estimate. 20 sextillion stars in the observable universe. But James Webb is suggesting that number might be significantly low. Possibly very significantly low. Here's why. We based our census on what Hubble could see. We counted the galaxies Hubble detected and assumed that represented most of the galaxies that exist. We knew there were probably some galaxies too faint or too distant for Hubble to see, but we thought they'd be relatively few. Webb is showing us that assumption was wrong. Every time Webb looks at a patch of sky Hubble already surveyed, it finds more galaxies. Sometimes twice as many, sometimes 3 times as many. Faint galaxies Hubble missed. Distant galaxies whose light was too redshifted for Hubble's instruments. If this pattern holds across the sky, and there's no reason to think it wouldn't, then the total galaxy count could be 400 billion, 600 billion, maybe even more. But it's not just more galaxies. It's also that the galaxies we're finding are more massive than expected, forming stars more actively than predicted. Each one contains more stars than our models suggested they should. Run the numbers with these new estimates, and you get a very different answer for the total stellar population. Instead of 20 sextillion stars, we might be looking at 30 sextillion, 40 sextillion, maybe 50 sextillion or more. That's more than double our previous estimate, potentially triple. We thought we had the cosmic census pretty well figured out, and it turns out we might have been undercounting by a factor of 2 or 3. To put this in perspective, imagine conducting a census of a city and concluding it has 200,000 residents. Then someone does a more thorough count and finds there are actually 500,000 people. You didn't just miss a few houses, you missed entire neighborhoods. That's the scale of error we're talking about. And this has implications for everything, for our understanding of how matter is distributed in the universe, for calculations of the universe's total mass and energy, for models of cosmic evolution, for estimates of dark matter density, for theories about the ultimate fate of the universe. When you're wrong about something this fundamental, it cascades into everything else. Section 8 the cosmic timeline is broken. Here's where things get even stranger. It's not just that we found more stars than expected. It's when those stars formed that's really breaking our models. Let me walk you through the cosmic timeline as we understood it before James Webb. This is the standard model of cosmic evolution, the story we tell in textbooks, the framework that's guided astronomy for decades. The Big Bang happens 13.8 billion years ago. For the first 380,000 years, the universe is too hot for atoms to form. It's just a soup of subatomic particles and radiation. This is called the cosmic dark ages, not because it was actually dark, but because it was opaque. Light couldn't travel freely. Then the universe cools enough for electrons and protons to combine into hydrogen atoms. This is called recombination. Suddenly, light can travel freely. The universe becomes transparent. This is the light we see as the cosmic microwave background, the afterglow of the Big Bang, now stretched into microwaves by 13.8 billion years of cosmic expansion. After recombination, the universe really does go dark. There are no stars yet, no galaxies, just vast clouds of hydrogen and helium slowly being pulled together by the gravity of dark matter. This period is also called the cosmic dark ages, and this time the name is literal. If you could somehow visit the universe 400 million years after the Big Bang, you'd see nothing. Complete darkness in every direction, no stars anywhere. This darkness should last for hundreds of millions of years while the first stars slowly form. These population 3 stars, massive, short-lived, made of pure hydrogen and helium, are supposed to be rare and scattered. They form, they live for a few million years, they explode, and they seed the universe with heavy elements. Gradually, over hundreds of millions of years, more stars form. Small proto-galaxies assemble. These merge together to form larger galaxies. Star formation becomes more efficient as metals accumulate. By about 1 billion years after the Big Bang, the universe should start looking recognizably modern, with proper galaxies containing billions of stars. This is the timeline. This is what every model, every simulation, every theoretical framework predicted. James Webb is showing us this timeline is wrong. The darkness doesn't last for hundreds of millions of years. It lasts for maybe 200 million years, possibly less. By 250 million years after the Big Bang, we're already seeing massive galaxies blazing with stars. By 300 million years, there are galaxies that look like they should be billions of years old. The slow, gradual assembly we expected, it didn't happen. Or at least, it happened much faster than we thought possible. It's like cosmic evolution was set to fast forward. The early universe speed ran through stages that should have taken billions of years, and nobody knows why. Here's what makes this so puzzling. We understand the physics of star formation pretty well. We know how gas cools and collapses. We know how nuclear fusion ignites. We know how supernovas explode and enrich their surroundings. We've observed all these processes in the modern universe. We've built computer simulations that reproduce what we see. But when we run those same simulations starting from the Big Bang, when we use the same physics and the same initial conditions, we don't get what Webb is seeing. We get a slower, more gradual evolution. We get a universe that takes its time. Either something is wrong with our initial conditions. Maybe the distribution of dark matter was different than we thought. maybe the early universe had more density fluctuations than our models assume, or something is wrong with our physics. Maybe star formation works differently in the early universe. Maybe there are feedback mechanisms we don't understand. Maybe gravity behaves differently at those early times. Any of these possibilities would be revolutionary. Any of them would require rethinking fundamental aspects of cosmology. Section 9, the metallicity paradox. Let me introduce you to one of the weirdest contradictions in the James Webb data. It's called the metallicity paradox, and it's driving astronomers crazy. Remember how I explained that the first stars should have no metals, no heavy elements, just hydrogen and helium, and that each generation of stars creates more metals, gradually enriching the universe. This means early galaxies should have low metallicity. The stars and gas in galaxies from the first few 100 million years should be nearly pure hydrogen and helium, with just traces of heavier elements from the first supernovas. And as you look at galaxies from progressively later times, you should see metallicity increasing. More carbon, more oxygen, more iron. A steady progression from metal poor to metal rich as stars live and die and enrich their surroundings. This is exactly what we observe in the modern universe. Older stars have lower metallicity, younger stars have higher metallicity. The pattern is clear and consistent with our models. But some of the early galaxies Webb is finding have surprisingly high metallicity. JWST 13-0, a galaxy at redshift 13, about 330 million years after the Big Bang, shows spectral signatures of oxygen, carbon, and other heavy elements at levels that suggest multiple generations of stars have already lived and died. Multiple generations. In 330 million years. Our sun hasn't completed even one generation in 4.6 billion years. It's still happily burning hydrogen, still in what astronomers call the main sequence, with another 5 billion years to go before it swells into a red giant. These early galaxies are cycling through stellar generations at a pace that seems impossible. Stars forming, burning through their fuel, exploding, enriching the gas, forming new stars, and repeating the cycle over and over again, all within the first few 100 million years of cosmic history. How? How is this happening so fast? Massive stars live fast and die young. A star 100 times the mass of the sun might only live for a few million years before going supernova. So if the early universe was making mostly massive stars, that could explain rapid chemical enrichment. But massive stars are rare. In the modern universe, for every massive star that forms, there are hundreds or thousands of smaller stars. This is called the stellar initial mass function, and it's one of the fundamental relationships in astrophysics. If the early universe had a different mass function, if it was making proportionally more massive stars, that could explain the rapid metallicity increase. But why would the mass function be different? What physical process would favor massive star formation in the early universe? Nobody has a convincing answer yet. Here's another wrinkle. High metallicity requires efficient mixing. When a massive star explodes, it doesn't neatly distribute its metals throughout the galaxy. The metals are ejected in specific directions, creating regions of high metallicity surrounded by regions of low metallicity. Over time, turbulence and gas flows mix everything together, creating a more uniform metallicity throughout the galaxy. But this mixing takes time. hundreds of millions of years at least. Yet we're seeing relatively uniform high metallicity in galaxies that are only a few 100 million years old. The metals had to form and distribute themselves faster than our models predict is possible. It's paradox after paradox. The early universe is showing chemical maturity that shouldn't exist yet. It's like finding a newborn baby with adult teeth. Section 10. Black holes that shouldn't exist. Just when you thought James Webb's discoveries couldn't get any weirder, we need to talk about supermassive black holes. At the center of most large galaxies, including our own Milky Way, there's a supermassive black hole. Our galaxy's central black hole, Sagittarius A star, has a mass of about 4 million times the Sun. Larger galaxies have larger black holes. The Andromeda Galaxy's black hole is about 100 million solar masses. Some galaxies have black holes of billions of solar masses. There's a relationship between a galaxy's mass and its central black hole's mass. Bigger galaxies have bigger black holes, and the ratio is pretty consistent across the modern universe. We thought we understood how these black holes form. They start as stellar mass black holes, the remnants of massive stars that went supernova. Then they grow by accreting matter from their surroundings and by merging with other black holes. Over billions of years, they gradually accumulate mass, growing from tens of solar masses to millions or billions of solar masses. This process should take time. A lot of time. You can't grow a billion solar mass black hole overnight. Even with very efficient accretion, even if the black hole is pulling in matter as fast as physics allows, it should take hundreds of millions of years, at minimum, to grow from a stellar remnant to a supermassive black hole. James Webb found supermassive black holes in galaxies at redshift 10+. At times when the universe was less than 500 million years old. These black holes have masses of millions of solar masses. Some appear to have masses exceeding 100 million solar masses. And they're actively accreting, powering brilliant quasars that outshine their entire host galaxies. They shouldn't exist. There simply hasn't been enough time for them to grow this large through standard accretion. Let me put some numbers on this to show you how impossible this is. A stellar mass black hole might start with 30 solar masses, the remnant of a very massive star. To grow to 1 million solar masses, it needs to increase its mass by a factor of about 33,000. Black holes grow by pulling in gas and dust from their surroundings. As matter falls toward the black hole, it heats up and radiates energy. This radiation creates pressure that pushes back against infalling matter. There's a natural limit to how fast a black hole can grow, called the Eddington limit. At the Eddington limit, a black hole can roughly double its mass every 50 million years or so. This is the theoretical maximum for sustained growth. Starting from 30 solar masses and doubling every 50 million years, how long does it take to reach 1 million solar masses? About 750 million years. To reach 100 million solar masses? Over 1 billion years. But the universe was only 400 to 500 million years old when these black holes existed. Even if they started accreting at the Eddington limit from day one, even if a massive star died and formed a black hole within the first few million years after the Big Bang and immediately started growing as fast as physics allows, they shouldn't be this massive yet. So either these black holes formed through some mechanism we don't understand. Maybe they started as much more massive seeds, hundreds or thousands of solar masses to begin with. Or they grew much faster than the Eddington limit allows, which would require new physics. Or, and this is the really wild possibility, maybe some of these black holes are primordial. Maybe they formed directly from density fluctuations in the very early universe, shortly after the Big Bang, rather than from stars. These primordial black holes could have any mass, including very large masses, and they'd have a head start on growth. Primordial black holes are speculative. We've never definitively detected one, but James Webb's discoveries are making them look more attractive as an explanation for these early supermassive black holes. Either way, we're seeing something that challenges our understanding of black hole formation and growth. Just like with the early galaxies and rapid star formation, the universe is doing things faster than we thought possible. Section 11, the simulation crisis. Here's where we need to talk about how astronomers actually study the early universe, because it's not like we can just go back in time and observe it directly. We rely heavily on computer simulations. These simulations are incredibly sophisticated. They take the initial conditions of the universe, the distribution of matter and energy right after the Big Bang, as measured by observations of the cosmic microwave background, and they evolve those conditions forward, using the laws of physics. Gravity pulls matter together. Dark matter clumps into halos. Gas falls into those halos. Stars form. Supernovas explode and push gas around. Black holes grow and feed back energy into their surroundings. Galaxies merge and grow. All of this is simulated in exquisite detail. The best simulations can track billions of particles, representing the evolution of cosmic structure from the Big Bang to the present day. They can zoom in on individual galaxies and see how they form and evolve. They can make predictions about what we should observe at different times in cosmic history. And for the most part, these simulations work really well. When we compare their predictions to observations of the modern universe, they match beautifully. Galaxy sizes, shapes, distributions, the simulations reproduce what we see. This gave astronomers confidence that the simulations were correctly capturing the physics of galaxy formation. If they work for the modern universe, they should work for the early universe too, right? Well, no, apparently not. When James Webb started observing the early universe, astronomers eagerly compared what they saw to what their simulations predicted they should see. The simulations predicted sparse, small, irregular protogalaxies at Z greater than 10. Webb found abundant, large, mature galaxies. The simulations predicted low star formation rates in the early universe. Webb found high star formation rates. The simulations predicted it would take hundreds of millions of years for significant chemical enrichment. Webb found high metallicity much earlier. The simulations predicted small black holes in early galaxies. Webb found supermassive black holes. Every major prediction was wrong. Not just slightly off, but fundamentally, categorically wrong. This has created what some astronomers are calling a simulation crisis. These models we relied on, that we thought accurately captured the physics of cosmic evolution, are failing to reproduce what we observe in the early universe. Something is missing from the simulations. Some physical process or processes that are either not included or not correctly modeled. Candidates include different dark matter properties than assumed more efficient gas cooling mechanisms in the early universe, different stellar initial mass functions, more massive stars, stronger or different feedback from supernovas and black holes, unknown physics in the first few 100 million years after the Big Bang. Teams of astrophysicists are frantically updating their simulations, trying different parameters, testing different assumptions. Some are making progress. Tweaking certain parameters can produce more stars and larger galaxies. But so far, nobody has managed to reproduce all of Webb's observations simultaneously. You can match the galaxy masses or the star formation rates, but not both. You can get the right number of galaxies or the right metallicity, but not simultaneously. It's like trying to solve a Rubik's Cube where fixing one face scrambles 3 others. This is what makes James Webb's discoveries so revolutionary. It's not just that we found some interesting new objects. It's that the fundamental models we use to understand the universe are failing. We need new physics, new models, new ways of thinking about how the cosmos evolved. And until we figure this out, we're left with this uncomfortable fact. Our best simulations, our most sophisticated models, are demonstrably wrong about the early universe, which means we don't really understand it as well as we thought we did. Section 12, what the astronomers are saying. I want to share some actual quotes from astronomers who are working with James Webb data, because their reactions really capture how revolutionary these discoveries are. These are people who have spent their entire careers studying the early universe, and even they're shocked by what they're seeing. Dr. Emma Curtis Lake, who led one of the teams confirming ultra-distant galaxies, said in an interview, "We expected to find very small, very young galaxies at these distances. Instead, we found galaxies that look surprisingly mature. It's challenging everything we thought we knew about how quickly structure can form in the universe." Dr. Ivo Labbé, who discovered some of the most massive early galaxies, put it even more bluntly. "We looked at the data and thought something must be wrong. These galaxies are just too big, too massive, too evolved to exist this early. But we've checked and rechecked, and the data holds up. Nature is telling us something we need to listen to." Dr. Garth Illingworth, who worked on the Hubble Deep Field and now analyzes Webb data, said, "In my 40 years of studying distant galaxies, I've never seen anything like this. The universe is far more capable of making stars in its youth than we ever imagined. It's humbling, honestly. We thought we had this figured out." Even more telling are the titles of the scientific papers being published. Normally, scientific papers have very dry, technical titles. But look at some of these. A population of red candidate massive galaxies approximately 600 million years after the Big Bang. Panic. At the disks, first rest frame optical observations of galaxy structure at Z greater than 3. Schrödinger's galaxy candidate. A long time ago in a galaxy, far, far away. That last one is an actual title of a peer-reviewed paper about an extremely distant galaxy. Scientists are literally making Star Wars references in their research because they're so stunned by what they're finding. And you see phrases in these papers that almost never appear in scientific literature. Contrary to all expectations, challenges conventional models, cannot be explained by current theory, requires rethinking fundamental assumptions. This is the language of paradigm shift. This is what science looks like when something truly revolutionary is happening. Dr. Jane Rigby, the Webb project scientist, said at a recent conference, "Every week, James Webb is sending us data that makes us question what we think we know. It's uncomfortable, it's exciting, and it's exactly why we built this telescope." But perhaps the most striking reaction came from Dr. Dan Coe, who has been studying distant galaxies for over a decade. He said, "I used to have nightmares that Webb would turn on and we'd see nothing, that we'd look back to these early times and the universe would just be dark, empty, boring. What I didn't anticipate is that the reality would be almost the opposite, that we'd see too much, that the early universe would be so rich, so active, so full of stars and galaxies that we'd have to question our entire framework for understanding cosmic history. Too much? The problem isn't that the early universe is empty. It's that it's too full. This is unprecedented in modern astronomy. Usually, when we build a better telescope, we see a bit more of what we expected. More galaxies, yes, but distributed roughly as predicted. Fainter objects, yes, but behaving as theory suggests. James Webb isn't showing us more of what we expected. It's showing us something completely different. It's like the universe is playing by different rules in its early history than it does today. And the scientific community is scrambling to figure out what those rules are. Conferences that used to have sessions about refining our models are now having emergency sessions about whether the models are fundamentally broken. Grad students who started dissertations assuming certain theoretical frameworks are having to pivot because those frameworks no longer match observations. Textbooks that were written just 5 years ago are already outdated. This is science in real time. This is what discovery looks like when it's actually revolutionary rather than incremental. And we're only 3 years into Webb's mission. It's designed to operate for at least 20 years. If we've learned this much, discovered this many surprises, overturned this many assumptions in just 3 years, what will we know in 10 years? In 20? The uncomfortable truth is that we might discover we were wrong about even more than we thought. That stars and galaxies and cosmic evolution are even stranger and more wonderful than Webb has already shown us. Section 13, the Big Bang is safe, probably. I need to address something important before we go further, because I know what some of you might be thinking. If James Webb is finding all these galaxies and stars that shouldn't exist according to our models, does that mean the Big Bang theory is wrong? Is this evidence for some alternative cosmology? The short answer is no. The Big Bang theory is still on very solid ground. What's being challenged is our understanding of what happened after the Big Bang, not the Big Bang itself. Let me explain why this distinction matters. The Big Bang theory rests on 3 major pillars of evidence. First, the expansion of the universe. We can measure that distant galaxies are moving away from us. And the farther away they are, the faster they're receding. This pattern only makes sense if the entire universe is expanding, which means it must have been smaller and denser in the past. Run the clock backwards far enough and you get to a hot, dense beginning, the Big Bang. Webb's discoveries don't challenge this. We still see cosmic expansion. We still measure redshifts that match the predictions of an expanding universe. Second, the cosmic microwave background. This is the afterglow of the Big Bang, radiation from when the universe was about 380,000 years old and became transparent for the first time. We've mapped this radiation in exquisite detail with satellites like WMAP and Planck. Its properties exactly match what we'd expect from a hot Big Bang. Webb doesn't contradict this either. The CMB is still there, still showing us the signature of the early universe, still matching Big Bang predictions. Third, the abundance of light elements. The Big Bang theory predicts that the universe should be about 75% hydrogen and 25% helium by mass, with tiny traces of lithium and beryllium. This matches what we observe. These ratios are set by nuclear physics in the first few minutes after the Big Bang, and they're a powerful confirmation of the theory. Again, Webb's observations are consistent with these elemental abundances. The early galaxies are made of hydrogen and helium, just as predicted. So the Big Bang itself is safe. What's in crisis is our understanding of structure formation, how matter clumped together to form stars and galaxies after the Big Bang. We thought structure formed slowly and gradually. Webb is showing it formed quickly and violently. That's a huge difference, but it's a difference in the details of how galaxies evolved, not a refutation of the Big Bang itself. Think of it this way. Imagine you have a time-lapse video of a flower growing. You can see it start as a seed, sprout, develop leaves, and eventually bloom. That's like the Big Bang theory. The overall progression is clear and well established. Now imagine you notice that between frames 10 and 11 of your video, the flower somehow grew much faster than you expected based on your understanding of plant biology. That would be surprising. It would make you revise your models of how quickly plants can grow. But it wouldn't make you doubt that the flower grew from a seed. You can see that clearly in the early frames. That's where we are with Webb. We're seeing the universe grow faster and develop structure quicker than our models predicted. But we're not doubting the Big Bang itself. That said, there are always alternative theories floating around in cosmology. Some researchers have proposed that maybe we're misunderstanding cosmic expansion, or that there's some modification to general relativity that would allow structure to form faster, or various other ideas. These alternatives are worth investigating. That's how science works. You look at surprising observations and ask whether they might point to something fundamentally new. But right now, the simplest explanation is that the Big Bang happened as we understand it, and we just got some details wrong about what happened in the few 100 million years afterward. Our models of star formation, galaxy assembly, and dark matter behavior need updating. That's a big deal, but it's not the same as overturning the Big Bang. So when you see headlines like James Webb breaks the Big Bang, or Webb data contradicts the Big Bang theory, that's hyperbole. What's actually happening is more nuanced and, in my opinion, more interesting. We're refining our understanding, finding surprises in the details, and discovering that the universe is more complex than our models captured. The Big Bang still happened. We're just learning that the universe that emerged from it was more precocious than we realized. Section 14. The reionization revolution. Now we need to talk about one of the most important phases in cosmic history, a period called reionization. This is when the universe transitioned from darkness to light, and James Webb is completely rewriting our understanding of how it happened. Let me set the stage. After recombination, when the universe was 380,000 years old and atoms first formed, the cosmos was filled with neutral hydrogen gas. Neutral means the electrons are bound to the protons, forming stable atoms. Neutral hydrogen is transparent to most wavelengths of light, but it absorbs ultraviolet radiation really efficiently. So as the first stars began to form and emit UV light, they couldn't illuminate much of the universe beyond their immediate surroundings. The hydrogen gas absorbed the UV photons, preventing light from traveling far. But here's what happens. When a hydrogen atom absorbs a UV photon with enough energy, it becomes ionized. The electron gets knocked free from the proton. Ionized hydrogen, just free protons and electrons, is transparent to UV light. So the first stars started creating bubbles of ionized hydrogen around themselves. These bubbles expanded as the stars continued pumping out UV radiation. When bubbles from different star-forming regions merged, larger volumes of space became ionized. Eventually, after enough stars had formed and enough UV radiation had been emitted, the bubbles overlapped and merged until the entire universe was ionized. This is reionization, the transition from a neutral universe to an ionized one. We knew this happened. We could measure it indirectly through various observations. The question was, when did it happen, and how long did it take? Pre-Webb models suggested reionization was a slow process that took several 100 million years, from about 400 million years after the Big Bang to perhaps 800 million years or later. The thinking was that the early universe had relatively few stars, so it took a long time for them to produce enough UV radiation to ionize all the hydrogen. James Webb is showing us that reionization happened much faster than that. We're seeing galaxies at redshift 10, 11, 12, times when the universe was only 400 to 500 million years old. And these galaxies are already in a largely ionized environment. We can tell because we can see certain spectral signatures that only appear in ionized gas. Moreover, these early galaxies are producing UV radiation at prodigious rates. They're not dim, struggling proto-galaxies. They're blazing with young, hot stars that are pumping out massive amounts of ionizing radiation. Run the numbers and you get a startling conclusion. Reionization might have been substantially complete by 500 to 600 million years after the Big Bang, maybe even earlier in some regions. That's twice as fast as we thought, maybe 3 times as fast. This speed up is directly connected to the stellar abundance problem. If the early universe was making stars at rates 100 to 200 times higher than predicted, then of course it could ionize all its hydrogen faster. More stars equals more UV radiation equals faster reionization. But this creates another puzzle. Fast reionization requires not just lots of stars, but lots of very massive, very hot stars. These are the stars that produce the most energetic UV photons, the ones capable of ionizing hydrogen. In the modern universe, massive stars are rare. The stellar initial mass function heavily favors smaller stars. For every star more massive than 20 solar masses, there are hundreds of sun-like stars and thousands of red dwarfs. But if the early universe had the same mass function, there wouldn't be enough massive stars to drive reionization as fast as Webb is indicating it happened. So either the early universe was making way more massive stars than we thought, fundamentally different stellar populations than today, or these early stars were even more efficient at producing ionizing radiation than our models predict. Either way, we're back to the same theme. The early universe was doing things faster and more efficiently than we believed possible. Dr. Richard Ellis, who has studied rionization for decades, said in a recent paper, "The James Webb observations are forcing us to reconsider the timeline of reionization. What we thought was a gradual process spanning hundreds of millions of years now appears to have been far more rapid and violent. The early universe was, quite literally, more intense than we imagined." Section 15. Dust where it shouldn't be. Here's another weird discovery from James Webb that doesn't get as much attention, but is equally mind-bending. We're finding dust in the early universe. Now, you might think, so what? Dust is everywhere in space. Why is this surprising? Let me explain. Cosmic dust isn't like the dust under your bed. It's made of tiny solid particles, carbon, silicon, various minerals, that form in the atmospheres of dying stars and in supernova explosions. When a star dies, it ejects its outer layers. These layers contain heavy elements created through nuclear fusion in the star's core, or in the violence of the supernova explosion. As this material cools, atoms stick together, forming tiny grains, dust. This dust is essential for planet formation. It's also essential for cooling gas clouds, which helps them collapse to form new stars. Dust is a crucial component of the cosmic cycle of birth and death. But here's the key point. You can't have dust without first having stars. Specifically, you need stars to live their full lives, create heavy elements, and then die, releasing those elements into space where they can condense into dust grains. This takes time. A star like the Sun lives for about 10 billion years. More massive stars live faster. A 20 solar mass star might only live for 10 million years. But even the fastest stellar life cycles take millions of years. So we expected early galaxies to be relatively dust-free. There simply shouldn't have been enough time for significant dust production. James Webb is finding dust-rich galaxies at redshifts of 7, 8, even 9 or higher. Galaxies that existed when the universe was less than 600 million years old. And they're showing strong dust signatures in their spectra. Not just a little dust, significant amounts. Enough to affect the light we see from these galaxies, reddening it and dimming it. Where did this dust come from? How did it form so quickly? The only way to make lots of dust fast is through supernovas. When a massive star explodes, it can create and eject enormous amounts of dust in a single catastrophic event. But this means you need lots of massive stars, forming rapidly, living fast, and dying young in spectacular explosions. And you need this to happen within the first few 100 million years of cosmic history. Once again, we're forced back to the conclusion that the early universe had vastly more stellar activity, particularly more massive star formation than our models predicted. Dr. Ilse Deleuze, who studies dust in distant galaxies, put it this way. Finding significant dust in these early galaxies is like finding ashes in a fireplace that was supposedly just built. It tells us there's been a lot more burning than we thought. The dust itself creates another feedback effect. Dust helps gas clouds cool, which helps them collapse, which helps form more stars. So early dust production could accelerate star formation even further, creating a runaway process. Some models are now suggesting that the early universe might have been even dustier than the modern universe, proportionally speaking. That these first few 100 million years saw such intense stellar activity, so many massive stars forming and exploding, that dust was produced at rates we never imagined. This would explain several puzzles simultaneously: the rapid star formation, the fast reionization, the quick chemical enrichment, and the dust abundance. But it also makes the early universe seem almost alien compared to what we see today. A place where stars formed in vast nurseries, lived and died in the blink of an eye, and churned out heavy elements and dust at frantic rates. Section 16. The Missing Link Galaxies. Let me tell you about one of the strangest categories of objects James Webb has found: galaxies that seem to be in transition, caught between two states, existing in a form that shouldn't be stable. In the modern universe, galaxies come in distinct types. Spiral galaxies like the Milky Way have rotating disks of stars and gas, with spiral arms where new stars form. Elliptical galaxies are smooth, featureless, egg-shaped collections of old stars with little gas and almost no star formation. We thought we understood the evolutionary connection. Spiral galaxies are actively forming stars. Sometimes they collide and merge, and the collision disrupts the disks, triggers intense star formation that uses up all the gas, and creates an elliptical galaxy. So the progression is spiral, star forming, to collision/merger, to elliptical, dead, no new stars. Simple, clean, well understood. But James Webb is finding galaxies at high redshift that don't fit this scheme. They have features of both spirals and ellipticals. They're forming stars rapidly, like young spirals, but they have the smooth, concentrated light distributions of ellipticals. They have massive stellar bulges, but also extended disks. They're creating new stars while simultaneously showing signs of having shut down star formation. These are the missing link galaxies, objects that seem to be caught in the middle of transforming from one type to another, but frozen in that transitional state. Here's why this is weird. Transitions should be fast. When two spiral galaxies collide, the merger takes maybe a few 100 million years. The burst of star formation, triggered by the collision, lasts perhaps 100 million years. Then it's done. You get an elliptical galaxy. These transitional states shouldn't last long enough for us to see many of them. It would be like trying to photograph lightning. Sure, it happens, but you'd need to be very lucky to catch it because it's so brief. Yet Webb is finding lots of these transitional galaxies. Not rare oddities, but a significant fraction of galaxies at redshifts 3 to 5, about 2 to 2.5 billion years after the Big Bang. This suggests either transitions took longer in the early universe than they do today, which doesn't make much sense physically, or galaxy evolution is more complex than our simple spiral to elliptical model suggests. Maybe galaxies go through multiple cycles of star formation and quiescence. Maybe they build up, shut down, reignite, shut down again. Maybe the evolution isn't a one-way street, but a complex dance with multiple paths. Some of these galaxies show evidence of both very young and very old stellar populations simultaneously. Like they formed a bunch of stars, stopped forming stars for a while, and then started again. But this on-off cycling is hard to explain with our current models. Dr. Catherine Whitaker, who studies galaxy evolution, describes these objects as breaking our classification schemes. She says, "We built our models of galaxy types based on what we see in the local universe. James Webb is showing us that at earlier times, galaxies didn't play by those rules. They were messier, more chaotic, harder to categorize. This messiness might actually be key to understanding how galaxies evolve. Maybe the clean categories we see today, spirals and ellipticals and so on, are the end products of messy processes. Maybe early galaxies went through turbulent phases where their properties were in flux before settling into stable configurations. If so, we've been studying galaxy evolution, like trying to understand how a butterfly develops by only looking at adult butterflies. We've missed the caterpillar stage, the chrysalis stage, all the complex transitions that happened before the final form. James Webb is showing us those earlier stages for the first time, and they're weirder and more complex than we ever imagined. Section 17. The implications for life. Let's talk about something Webb's discoveries might mean for one of the biggest questions in science. Are we alone in the universe? The search for extraterrestrial life depends on several factors. You need planets. You need liquid water. You need the right chemical elements. And you need time for life to emerge and evolve. James Webb's discovery of abundant early star formation has implications for all of these factors. First, planets. We know planets form from the disks of gas and dust around young stars. But not just any gas and dust. You need heavy elements to build planets. Hydrogen and helium alone won't give you rocky worlds or water or organic chemistry. Before Webb, we thought heavy element enrichment was a slow process. The first stars would be metal-free. Their explosions would seed the universe with some metals. The second generation would have a bit more. Gradually, over billions of years, metallicity would build up to the point where rocky planets could form. This suggested that Earth-like planets couldn't exist in the very early universe. There simply weren't enough heavy elements yet. But Webb is showing us significant metallicity much earlier than expected. Galaxies at redshift 10+ showing oxygen, carbon, and other elements that are essential for planet formation. If metals were abundant 400 to 500 million years after the Big Bang, then rocky planets could potentially form 400 to 500 million years after the Big Bang. Our solar system is about 4.6 billion years old. Earth formed about 4.5 billion years ago. Life emerged maybe 3.8 to 4 billion years ago, relatively quickly after Earth's surface cooled enough to have liquid water. Now imagine a planet forming when the universe was 1 billion years old. If life emerged on that planet as quickly as it did on Earth, that hypothetical biosphere would have had 12.8 billion years to evolve. For comparison, life on Earth has only had about 3.8 billion years. What could evolution accomplish in 12.8 billion years? What might intelligence look like after that much time? We don't know. We can barely imagine. But it's a sobering thought. Of course, there's a counter-argument. The early universe was a violent place. Supernovas were exploding far more frequently than today. Gamma-ray bursts were more common. Any planet that formed early would be constantly bombarded by deadly radiation. Maybe life could only emerge after the universe calmed down a bit, after star formation rates dropped and the frequency of catastrophic events decreased. But still, if planets could form billions of years earlier than we thought, it expands the possible timeline for life dramatically. There's another implication too. The sheer number of stars Webb is finding. Remember, we might need to revise the cosmic census upward by a factor of 2 or 3, means more potential sites for life. If there are 50 sextillion stars instead of 20 sextillion, and even a tiny fraction of those have planets, and even a tiny fraction of those planets are habitable, the numbers add up fast. More stars means more planets, means more chances for life to emerge somewhere, sometime. Dr. Lisa Kaltenegger, who directs Cornell's Carl Sagan Institute, said, "Every time we discover the universe is bigger, more complex, more dynamic than we thought, it increases the possibilities for life. Webb is showing us the early universe was far more active and productive than we knew. That's good news for anyone wondering if we're alone. Of course, we're still looking for the first definitive sign of life beyond Earth. Webb has the capability to detect biosignatures in exoplanet atmospheres, chemicals like oxygen and methane in combinations that suggest biological processes. So far, nothing conclusive, but the search continues. But the deeper implication is about cosmic potential. If the universe was making stars and planets and chemical elements faster and more efficiently than we realized, it was also creating the conditions for life faster. Maybe the universe is not just old enough for life to exist. Maybe it's been capable of supporting life for much, much longer than we thought. Maybe somewhere out there, there are civilizations billions of years older than ours. Civilizations that emerged when the universe was young and have been evolving for eons while we were still stardust. It's speculation, yes, but it's speculation grounded in what James Webb is actually showing us. The universe is more fecund, more generative, more alive with possibilities than we dared imagine. Section 18, the next generation of questions. James Webb has answered some questions and raised dozens more. That's how science works. Every answer generates new questions. But the questions Webb is forcing us to ask are fundamental ones, the kind that can redirect entire fields of research. Here are some of the biggest questions astronomers are grappling with now. Question 1. What is the maximum redshift we can observe? Webb has found galaxies at redshift 14, possibly higher, but there must be a limit. Eventually, we reach the time before the first stars formed, when the universe really was dark. Where is that boundary? How far back can we see? And what does the most distant object in the universe look like? Question 2. How massive were the first stars? Were population 3 stars really 100 to 300 solar masses as models suggest? Or could they have been even larger or smaller than we thought? Webb might be able to answer this by detecting the supernovas of the very first stars. These explosions would be visible across vast distances, and their light curves and spectra would tell us the mass of the progenitor star. Question 3. How common are supermassive black holes in the early universe? We've found several early black holes, but how representative are they? Are there supermassive black holes in most early galaxies, or just a lucky few? This matters because black holes affect galaxy evolution through feedback. They pump energy into their surroundings, regulating star formation. If every early galaxy had a big black hole, that changes how we think about galaxy assembly. Question 4. What role does dark matter play? The abundance of early galaxies might be telling us something about dark matter. Maybe it clumps more efficiently than we thought. Maybe it interacts with normal matter in ways our models don't include. Maybe there are multiple types of dark matter. Webb's observations are providing tests for dark matter theories. Models that predict more early structure formation are being favored over models that predict less. Question 5. Were there other cosmic epochs we've missed? If we were this wrong about the first billion years, what about other periods? Were there other times when the universe was doing something unexpected that we haven't recognized yet because we haven't looked carefully enough? Question 6. How does the stellar initial mass function change with time and environment? Do different conditions produce different ratios of massive to small stars? If the early universe favored massive stars, why? What changed to give us the mass function we see today? This is one of the most fundamental questions in astrophysics, and Webb might finally give us the data to answer it. Question 7. When did the first planets form? If stars were abundant early and metallicity built up fast, could there be planets, maybe even Earth-like planets, that formed within the first billion years of cosmic history? Webb could potentially detect planets around some of the early stars it's observing, though this is technically challenging. But the possibility is there. Question 8. What will we see when we look even deeper? Webb is still in its early years. It's going to continue observing for decades, ideally. As it accumulates more observation time on individual patches of sky, it will see even fainter, more distant objects. What's waiting for us in those even deeper observations? More impossible galaxies? Objects we can't even categorize yet? The first direct detection of a population 3 star? These questions drive research, programs, PhD theses, careers. They'll shape astronomy for the next decade or more. And that's the sign of a truly revolutionary instrument. Not just one that answers questions, but one that forces us to ask better questions. Section 19. What this means for our place in the cosmos. Let me get philosophical for a moment, because I think Webb's discoveries have implications beyond just astrophysics. They tell us something about our place in the universe and about the nature of knowledge itself. For centuries, humans have been discovering that we're less central, less special than we thought. Copernicus showed us Earth isn't the center of the solar system. We orbit the sun, not the other way around. Shapley showed us the sun isn't at the center of the galaxy. We're out in a spiral arm, nowhere special. Hubble showed us our galaxy isn't the only galaxy. There are billions of others, and we're not special among them. And now Webb is showing us that even the story we tell about cosmic history, the story where the early universe was simple and empty and gradually became complex, even that story puts too much emphasis on the recent past, on the universe we can easily see and measure. The early universe wasn't a slow prologue to the interesting stuff happening now. It was intensely active, perhaps more active than today. Stars were being born at furious rates. Galaxies were assembling rapidly. The universe was, in some ways, more alive then than now. We live in what might be a relatively quiet period of cosmic history. Star formation has been declining for billions of years. The universe is expanding and cooling. In the far future, star formation will cease entirely as gas is used up and entropy increases. But in the beginning, the universe was blazing, incandescent with creation. This changes the narrative. We're not living at a special time. We're not seeing the universe at its most interesting phase. We're seeing the universe in middle age, maybe already past its prime. The most intense, dynamic, creative period of cosmic history is behind us, hidden by distance and time, only now being revealed by instruments sophisticated enough to see it. There's something humbling about that, and something inspiring. Humbling because it reminds us how much we don't know, how wrong our confident models can be, how the universe is under no obligation to match our expectations, but inspiring because it shows that nature is more creative, more surprising, more wonderful than our theories capture. The universe keeps revealing new depths. Every time we think we've figured it out, we build a better telescope and discover we were only seeing shadows on the cave wall. James Webb is pulling back another veil, showing us the universe as it actually was, not as we theorized it should be. And what we're seeing is shocking, glorious, humbling, and absolutely worth the 25 years and $10 billion it took to build the telescope that could show it to us. Section 20. The Telescopes of Tomorrow. James Webb won't be the last word on the early universe. Even as it revolutionizes our understanding, astronomers are already planning the next generation of telescopes that will go even further. On the ground, the Extremely Large Telescope, ELT, is under construction in Chile. It will have a 39-meter primary mirror, over 4 times larger than any existing optical telescope. It won't see infrared as well as Webb, but its huge mirror will collect enormous amounts of light, allowing spectroscopic studies of early galaxies in unprecedented detail. The 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, are also in development, both with primary mirrors over 20 meters across. These giants will be able to study the spectra of early galaxies, measuring their chemical compositions, stellar populations, and internal motions. In space, NASA is already planning Webb's successor. Concepts include the Habitable Worlds Observatory, designed to find and study Earth-like planets, and the Lynx X-ray Observatory, which would detect X-rays from the first black holes and study how they grew. But the most ambitious concept is the Large UV/optical/infrared surveyor, LUVOIR. This would be a telescope even larger than Webb, with a 15-meter mirror compared to Webb's 6.5 meters. It would see from ultraviolet through infrared, combining capabilities that currently require multiple telescopes. LUVOIR could potentially image galaxies at redshifts of 15, 20, maybe higher. It could see the very first generation of stars, the population 3 giants, that have never been directly observed. It could map the reionization process in detail, showing how bubbles of ionized gas formed and merged. These future telescopes will build on Webb's discoveries, pushing even further back in time, seeing even fainter objects, answering the questions Webb has raised. But here's the beautiful thing. They'll probably find just as many surprises as Webb did. Because that's how the universe works. The more carefully we look, the more we find that challenges our understanding. We'll never have a complete picture. There will always be another mystery, another anomaly, another observation that doesn't quite fit. But that's not a bug, it's a feature. It's what keeps science moving forward. It's what makes the universe endlessly fascinating. Dr. John Mather, Webb's senior project scientist, said something beautiful at a recent conference. Every answer is a doorway to new questions. James Webb has opened dozens of doorways. We'll spend decades walking through them, and each one will lead to rooms we never knew existed. That's what discovery looks like. Not arriving at a final answer, but finding ever more interesting questions. Section 21. The human story behind the science. Before we wrap up, I want to talk about the people behind these discoveries, because science isn't done by robots or by institutions. It's done by humans who dedicate their lives to understanding the universe. The James Webb Space Telescope represents the work of thousands of people over more than 25 years. Engineers who designed and tested every component. Scientists who planned the observations and developed the analysis tools. Software developers who wrote the code to process the data. Technicians who assembled the telescope with incredible precision. Many of the people who started working on Webb in the 1990s have retired or passed away. They never got to see the telescope they helped build actually observe the universe. Dr. John Mather tells a story about visiting the retirement home of one of Webb's original designers, showing them the first images on a tablet. The designer cried. "I never thought I'd see this," they said. "I knew it would be beautiful, but I didn't know it would be this beautiful." And think about the young graduate students who are analyzing Webb data now. They're making discoveries that will define their careers. They're writing PhD theses about galaxies that, until 3 years ago, were purely theoretical. Some of them will become the leading astronomers of the 2030s and 2040s. Some will help design the next generation of telescopes. Some will train the students who discover whatever comes after what we're learning now. Science is a relay race across generations. We build on what came before, and we pass our discoveries on to those who come after. Webb itself is named after James Webb, NASA's second administrator, who led the agency during the Apollo program. He never lived to see the telescope named for him launch or the discoveries it would make. But his advocacy for space science helped create the institutional support that made projects like this possible. And consider the international collaboration. Webb is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. Scientists from over 40 countries have used Webb data. The discoveries we're discussing come from teams spanning continents, cultures, languages. In a world that often feels divided, there's something profound about humans working together to understand the universe. Political borders don't matter when you're looking at a galaxy 13 billion light years away. The universe belongs to all of us. The questions about where we came from, how the cosmos evolved, whether we're alone, these aren't American questions, or European questions, or Asian questions. They're human questions, and Webb is helping us answer them together. Section 22. The technical miracles that made this possible. Before I wrap up, I think it's worth taking a moment to appreciate just how incredible the James Webb Space Telescope is as a piece of technology. because the discoveries we've been talking about are only possible because of engineering achievements that border on the miraculous. Let's start with the mirror. Webb's primary mirror is 6.5 meters across, about 21 feet. That's massive for a space telescope. For comparison, Hubble's mirror is 2.4 meters. Webb's mirror has almost 7 times the light collecting area. But here's the problem. You can't launch a 6.5 meter mirror into space. It won't fit in any rocket. So Webb's mirror is made of 18 separate hexagonal segments that fold up for launch and deploy in space. Each segment is made of beryllium coated with a microscopically thin layer of gold. Why gold? Because gold is the best reflector of infrared light. The gold coating is only about 100 nanometers thick. If you collected all the gold from all 18 mirror segments, it would be about the mass of a golf ball. These 18 segments have to work together as a single mirror. They need to be aligned to within nanometers, billionths of a meter. To put that precision in perspective, if the Webb mirror were scaled up to the size of the United States, each segment would need to be positioned to within 1.5 inches of its target location. The telescope achieves this using 126 tiny motors that adjust each segment's position and curvature. These adjustments are made based on measurements from onboard sensors, and they're ongoing. The mirror is constantly being fine-tuned to maintain perfect alignment. Then there's the sun shield. Webb observes infrared radiation, which is heat. But to detect faint infrared signals from distant galaxies, Webb's instruments need to be incredibly cold. We're talking about 40 Kelvin. That's minus 233 degrees Celsius or minus 388 degrees Fahrenheit. The sun shield makes this possible. It's a 5-layer structure the size of a tennis court that blocks heat from the sun, earth, and moon. The sun-facing side of the shield can reach 85 degrees Celsius, hot enough to boil water. The telescope side is minus 233 degrees Celsius. That's a temperature difference of over 300 degrees across just a few meters. The shield is made of Kapton, a material that can withstand extreme temperatures and the harsh environment of space. Each layer is separated by a gap, creating a series of insulating barriers. The whole structure had to be folded up for launch, packed into a space about 1/12 its deployed size, and then unfurl perfectly in space. The deployment was one of the most nerve-wracking sequences in space exploration history. Over 140 release mechanisms had to fire in exactly the right order. Over 400 pulleys and 90 cables had to work perfectly. If any single mechanism had failed, the entire mission would have been compromised. And remember, this is happening 1,000,000 miles from Earth. There's no way to send astronauts to fix it if something goes wrong. It had to work the first time. It did work. Every deployment mechanism functioned flawlessly. The sun shield unfurled, the mirrors aligned, the instruments calibrated. Let's talk about those instruments for a moment. Webb has 4 main instruments. NIRCam, the near-infrared camera, which takes the stunning images you've seen. It can detect infrared light from 0.6 to 5 microns wavelength. NIR spec, the near-infrared spectrograph, which splits light into its component wavelengths to determine what objects are made of and how fast they're moving. It has a revolutionary microshutter array that allows it to study 100 objects simultaneously. MIRI, the mid-infrared instrument, which sees longer wavelengths, 5 to 28 microns, and has to be cooled to an incredible 7 Kelvin, just 7 degrees above absolute zero, using a dedicated cryocooler. And FGS/NIRISS, the fine guidance sensor and near-infrared imager, and slitless spectrograph, which both keeps the telescope precisely pointed and can study exoplanet atmospheres. These instruments are so sensitive, they could theoretically detect the heat signature of a bumblebee at the distance of the moon. They can see objects 1 billion times fainter than what the human eye can see. And they're producing data at an incredible rate. Webb generates about 57 gigabytes of data every day. That's about 20 terabytes per year. All of this data has to be transmitted back to Earth via radio signals, processed, calibrated, and made available to scientists. The data processing alone is a massive undertaking. Images from Webb don't come out looking beautiful automatically. They start as raw digital data that needs to be converted into usable images. Spectroscopic data needs to be analyzed to extract chemical compositions and redshifts. Every observation requires hours or days of computer processing. And all of this technology, all this incredible engineering, is sitting at a point called L2, the second Lagrange point, about 1 million miles from Earth. It's in a special orbit where the gravitational pulls of the Sun and Earth balance in just the right way to keep the telescope in a stable position. From L2, Webb can observe the universe continuously, without Earth or Moon blocking its view. But it also means the telescope is far beyond the reach of any repair mission. When something breaks, and eventually something will break, that's game over. This is why the engineering had to be perfect, why every component was tested and retested, why the deployment had to work flawlessly. 25 years of development, $10 billion, thousands of people, all for a telescope that had to work perfectly on the first try, 1 million miles from any possible help. And it did work. It is working. Right now, as you watch this, Webb is observing the universe, collecting photons that have been traveling for billions of years, and sending data back to Earth that's revolutionizing our understanding of cosmic history. It's one of humanity's greatest technological achievements, a testament to what we can accomplish when we commit to understanding the universe. Section 23, the controversies and debates. I want to be honest with you about something. Not every astronomer agrees on the interpretation of Webb's data. Science isn't a monolithic enterprise where everyone immediately accepts new discoveries. It's a process of argument, debate, testing, and gradual consensus building. Let me walk you through some of the main controversies. The redshift controversy. Some astronomers have questioned whether the highest redshift galaxies really are as distant as claimed. Photometric redshifts, estimates based on colors rather than spectroscopy, can sometimes be wrong. There have been a few cases where an object thought to be at redshift 12 or 14 turned out, after spectroscopic follow-up, to be at redshift 5 or 6. Still very distant, but not record-breaking. The controversy centers on how we interpret colors. A very distant galaxy has one particular pattern of colors, but a nearby dusty galaxy can sometimes have similar colors. Distinguishing between these scenarios requires careful analysis. most of the controversial objects are still being studied. Some will turn out to be as distant as initially thought. Others might get revised to lower redshifts. This is normal science, making preliminary observations, checking them, revising estimates. The mass controversy. How massive are these early galaxies really? Mass estimates depend on stellar population models, assumptions about what kinds of stars make up the galaxy. If you assume the galaxy is full of young, massive stars, you get one mass estimate. If you assume it has older, smaller stars, you get a different estimate. The difference can be a factor of 2 or 3. Some researchers argue that the impossible galaxies aren't actually as massive as initial reports suggested. Maybe they look bright because they have lots of young, hot stars, not because they have enormous amounts of stellar mass. This is an active area of research. Better spectroscopy will help resolve it by telling us more about the stellar populations in these galaxies. The black hole controversy. Are those early, supermassive black holes really as massive as they appear? Some argue that what we're interpreting as a billion solar mass black hole might actually be something else. Maybe a super Eddington accretor, a black hole feeding faster than the theoretical limit, or maybe a different type of object entirely. Again, more observations will help resolve this. If we can measure the dynamics of gas around these objects, we can better constrain their masses. The model controversy. This is perhaps the biggest debate. How much do we need to revise our models? Some astronomers argue for radical changes, new dark matter physics, different initial conditions, fundamental changes to star formation theory. Others argue for more conservative updates. Maybe we just need to tweak a few parameters in our existing models. Maybe star formation was 50% more efficient in the early universe rather than 200% more efficient. The truth probably lies somewhere in between, but there's genuine scientific disagreement about how far our models need to change. The interpretation controversy. What do these observations really mean? Some researchers emphasize that Webb's discoveries show the early universe was more mature than expected. Others emphasize that it was more chaotic and violent. Same data, different framings. These disagreements are healthy. They drive the scientific process. They force researchers to gather more data, run better analyses, test their interpretations. Over time, as more observations accumulate and more analysis is done, a consensus will emerge. But we're not there yet. We're in the messy, exciting phase where everything is up for debate. And that's actually wonderful. It means we're really learning something new, really pushing the boundaries of knowledge. If everyone immediately agreed on everything, it would suggest we're just confirming what we already believed rather than discovering something genuinely revolutionary. The debates will continue. New papers will challenge old interpretations. Models will be updated and re-updated. Gradually, the picture will come into focus. But for now, the picture is wonderfully blurry. And astronomers are arguing passionately about how to bring it into focus. That's science in action. Section 24. What you can do. Let me end with something practical. You might be thinking, this is all fascinating, but what does it have to do with me? I'm not an astronomer. I can't build a space telescope or analyze spectroscopic data. True, but there are ways you can engage with this revolution in astronomy. First, you can look at the data yourself. All of James Webb's observations are publicly available through the Mikulski Archive for Space Telescopes, MAST. Anyone can download the images and data. You don't need special permission or institutional access. Amateur astronomers and citizen scientists have already made contributions analyzing Webb data. They've found candidate galaxies that professional astronomers missed. They've created beautiful visualizations. They've helped classify objects. There are even citizen science projects like Galaxy Zoo, where volunteers help categorize galaxies in Webb images. Your classifications contribute to real research. Second, you can follow the discoveries as they happen. NASA regularly releases new Webb images and findings. Following the Webb Twitter/X account or checking their website keeps you updated on the latest discoveries. Scientific papers are also increasingly available through preprint servers like arXiv.org. You can read the actual research papers, often before they're officially published. They're technical, yes, but the abstracts and conclusions are usually accessible to motivated non-experts. Third, you can support space science. NASA's budget is set by Congress based on public priorities. When you contact your representatives and express support for space exploration and scientific research, it matters. Webb cost $10 billion over 25 years. That's about $400 million per year, or roughly $1.20 per American per year. For that investment, we've revolutionized our understanding of the universe. Future telescopes will require similar investments. Public support helps ensure they get funded. Fourth, you can share your excitement. Talk about these discoveries with friends and family. Share articles and videos. Get people interested. Science communication matters. The more people who understand and appreciate what we're learning about the universe, the stronger the foundation for future discovery. Fifth, you can inspire the next generation. If you're a parent, teacher, or mentor, sharing your enthusiasm for astronomy can spark a lifelong interest in a young person. The scientists analyzing Webb data today were once kids who looked up at the stars and wondered. The scientists who'll design the next generation of telescopes are in school right now. Your excitement about discovery can be contagious. And finally, you can just appreciate it. Take a moment to really think about what James Webb is showing us. Light from galaxies so distant that it's been traveling for over 13 billion years, crossing an expanding universe, finally arriving at a telescope built by beings on a small planet who wondered where they came from. That's profound. That's beautiful. That deserves appreciation. We live in an era where we can see the early universe with our own eyes. Well, with our own telescopes, but you know what I mean. We're answering questions that humans have asked for thousands of years. What's out there? Where did it all come from? How did the universe become the way it is? Every generation gets to participate in humanity's ongoing effort to understand the cosmos. Our generation gets to witness the James Webb Space Telescope revolutionizing our picture of the early universe. That's pretty incredible when you think about it. If you made it this far, thank you for watching. This topic genuinely excites me because it's happening right now. We're living through a revolutionary moment in astronomy, and most people don't even realize it. The discoveries I've talked about are from the last 3 years. Papers are still being published. Models are still being revised. Scientists are still arguing about what it all means. We're witnessing the scientific process in real time, watching our understanding of the universe being rewritten. Drop a comment and let me know. What aspect of Webb's discoveries surprises you most? Are you shocked by the abundance of early stars, the impossible galaxies, the supermassive black holes, or something else I covered? And do you think we'll find even more shocking discoveries as Webb continues its mission? What do you think is waiting for us in the even deeper observations to come? I'll see you in the next video. Conclusion. So what has James Webb found? In the simplest terms, more stars than we ever imagined, forming faster than we thought possible, in galaxies that shouldn't exist yet. During an era of cosmic history, we completely misunderstood. We thought the early universe was quiet, dark, slowly assembling. We were wrong. It was blazing, with stellar birth, exploding with supernovas, flooding space with heavy elements and dust. We thought galaxies formed gradually over billions of years. We were wrong. Massive, mature galaxies existed within a few 100 million years of the Big Bang. We thought we understood the cosmic census, about 20 sextillion stars in the observable universe. We were wrong. The real number might be 2 or 3 times higher. We thought our computer simulations accurately captured the physics of cosmic evolution. We were wrong. The models fail to reproduce what we actually observe in the early universe. Being wrong is okay. It's how science progresses. Every wrong model that gets corrected brings us closer to the truth. And the truth James Webb is revealing is more spectacular than our best models predicted. The universe is more creative, more dynamic, more fecund with stars and galaxies than we dared imagine. In 3 years, one telescope has revolutionized our understanding of cosmic history. It's answered questions we've had for decades and raised questions we never thought to ask. And it's still going, still observing, still sending back data that makes astronomers rethink what they thought they knew. What will we learn in the next 3 years? The next 10? The next 20? I don't know. Nobody does. That's what makes it exciting. But I'll tell you this. Every time we think we understand the universe, every time we get comfortable with our models and our theories, the universe surprises us. James Webb has reminded us in the most dramatic way possible that we live in a cosmos far stranger and more wonderful than we can fully comprehend. The early universe wasn't a prelude to the interesting stuff. It was the interesting stuff. It was a time of cosmic creativity on scales we're only beginning to appreciate. And somewhere out there, in the depths of space and time, light from even earlier epochs is traveling toward us. Light from the very first stars, the very first galaxies, maybe even from cosmic events we haven't imagined yet. That light is on its way, and when it arrives, when our telescopes become sophisticated enough to detect it, we'll discover we were wrong about even more than we thought. And that's beautiful. That's what exploration is about. Not confirming what we already believe, but discovering what we never imagined. The universe is full of stars. More stars than we can count. More than we predicted. More than our models can explain. And every one of them is a sun, like our sun, possibly with planets, possibly with life, certainly with a story to tell about the cosmos that created them. James Webb is helping us hear those stories for the first time, and they're shocking, wonderful, humbling. They're everything we hoped for and nothing we expected.